All right, this is Mr. McCord's chemistry class. We're continuing on with more calculations using the gas laws. We're going to introduce a new tool into our tool belt using some of the pieces that we already have. So with Boyle's law and Charles' law and Gay-Lussac's law, not in order here, but shown up here, we have this kind of order of things. We've got kind of a before and an after with each of these equations. One's showing the before and two's showing the after. We seem to have a pattern of always keeping the p's and v's on top in the numerator whenever we do these calculations, and temperature always seems to be in the denominator on the bottom. So if I'm dealing with just pressure and just volume, Boyle's law has got me covered. If I've got just volume and just temperature, Charles' law is right there for me. But there are times when all three of those variables are going to change at the same time, especially in the real world. Okay, so if we kind of keep with this pattern that we've got here, we want our pressure to stay on top. We want our volume to stay on top. Right. They're next to each other just like in Boyle's law, so they're going to be multiplied together. All right. And just like in Gay-Lussac's law and Charles' law, in both cases, temperature should be below the pressure and the volume. Okay? And just like in all three of these gas laws, we should get the same equation on the other side of this equal sign. It should be the same setup. Only now it's going to be the kind of 2 version, the after the change version. So this version is really nothing new. It's just kind of crunched together so it's more usable in different cases. We call this the combined gas law. For obvious reasons, because we're combining other gas laws to get this one. Okay. Same considerations as before. Okay. We can use different units of pressure, like atmosphere, or mmHg, or kPa. We can use different units of volume, like liters or milliliters. We want to keep temperature in Kelvin. Okay. But we just have to make sure those units match on either side. All right. If we start in kPa, we want to end in kPa. If we start in milliliters, end in milliliters. Okay, so this gas law is just another thing we can add to our tool belt, like I said before, and it can also be useful if you don't have these original gas laws sitting around. If you don't have those equations, well, you can reduce this down to whatever you need. If I'm dealing with a balloon that is changing in volume and pressure, but the temperature stays the same, if I just ignore the temperature there and there, I just have Boyle's law. If I am working with, something like a rigid container, the volume's not changing, and I hide the volume here and here, Chris my heart here, then I get Gay-Lussac's law. All right? So you can go from the combined gas law and figure out the other gas laws if you need them. All right, let's do an example. So I've got one of these sort of metal cans here for lacquer thinner. You might have something sitting around your garage like this, maybe acetone or something like that. But I like doing examples with these metal cans because when capped tight, gas can't escape from them. So you've maybe got a little bit of air or a little bit of acetone or thinner, whatever, vapor floating around inside your can. And as the temperature around them changes, well, the gas has nowhere to go. So the pressure and the volume inside is going to change, along with it. So let's say I've got one of these out on a really cold night when, the weather just gets real bad. So my temperature drops, okay? It gets real cold, right? And I come in the morning and this can has been severely crushed in. It's like dented in. Okay, not because someone went and crushed it, but because the pressure and the volume of the gas inside changed. So we got a huge temperature change here going from 290 Kelvin to 2 degrees, but it's in Celsius. So we have two different temperature values here. So we're going to need to convert one of them. We want to do all our gas laws in Kelvin. So we're going to change our Celsius into Kelvin and see how that works out. So whenever you need to convert between Celsius and Kelvin, it's just changing by 273.15. Right? So we're just going to take 2 degrees Celsius and bump it up by 273.15 degrees. So 2 plus 273.15 is going to be a temperature of 275.15. And now we're in Kelvin. That's going to change our answer a lot, so be sure not to miss out on changing your temperatures from Celsius into Kelvin first. Okay? Other than that, since we have pressure and volume and temperature all changing in this problem, we need to use the combined gas law to put this all together. So let's set this up. Let's plug everything into our spots, our P1, V1, T1, and our P2 that we're looking for, our V2, and our T2. Okay, so we've got everything plugged into the combined gas law, all our P's and V's and T's, and we're looking for P2, so we've got to get that alone. Now, there are a couple ways you can do the math, and however you like to do your algebra, as long as you don't break any rules of math, go for it. I like to condense the numbers down, so I'm going to do that first. I'm going to take all this stuff over here that I can multiply and divide and do that and get something more workable. So I'm taking 758 millimeters of mercury times 3.785 liters divided by 290 Kelvin here. Right? So multiplying and dividing these numbers has not changed the units I have. So what I'm going to be left with is going to be a little weird. I still have mmHg and big L up on top. And I've got Kelvin on bottom. Right? It looks kind of weird having a unit with a fraction bar in it, but, whatever works. Just to show that these are together on the top and they're two separate units, I'm going to put a little multiplication dot in between them so you can see, two separate things. Okay? Now, hopefully, since we're solving for pressure, we should be able to pare this down to just the mmHg as our units cancel. Let's see. We're going to write the rest of this back out. Okay, so if I want to get P2 alone, I'm going to have to get rid of these. So to cancel them out, I've got to do the opposite of what I'm doing over here. Okay, and this is where sometimes it can get tricky. When you get to this point, you're halfway through, sometimes you just look at this and you're like, nice, okay. And then this is on bottom, so I'm dividing it over here. But in order to cancel, we got to do the other way around. If this is being divided over here, we want to multiply it on both sides to get it to cancel. So if you like just going in your calculator and not writing out the math as you go, that's something you might fall into, so be careful of that. So let's cancel these out. Okay. So our temperature, our 275.15, should cancel over here on the right. That's totally going away. Okay, and our units should cancel over here. Kelvin on top, Kelvin on bottom, cancel out. So we're left with just our mmHg and our liters units. Okay, Now again, I like to condense, so I'm going to multiply these numbers together and see what I get over here. Right. 275.15 times 9.89. All right, 2721.23-ish. So about 2,721. All right, so we got a big number on the left. It's going to be equal to still this P2 times 2.8 liters. We haven't messed with that yet. Okay, so our last step to get P2 alone is to divide off this 2.8 liters. I want to do that in different colors so it doesn't get all crowded in here. Let's do light blue. All right. 2.8 cancels out. And my liters unit cancels out. Okay. So all I have to do now is divide my 2,721.23 divided by 2.8 and see what my P2 comes out to be. This is going to be kind of low. Hopefully it'll fit. Got about 971.87, and my unit left should be mmHg, which is what I want for a pressure unit in this case. All right, so that's my answer. Something else to watch out for. You might have problems like this that look the same, but you're looking for an original variable. That just means you're looking for a P1 or a V1 or a T1. The math is the same. It's just going to be, solving out to get something on the left side instead of the right. Okay? So if you see that new variable versus original variable, don't freak out. It's not something totally new. I'm not throwing you a weird curveball. As long as you're putting stuff in the right place in your equation, it's going to work out. Okay?